Welcome back. We got momentum worksheet number 1 and problem number 3 here. An astronaut floating at rest in space whose mass is 80 kilograms excuse me, carries an empty oxygen tank with a mass of 10 kilograms. He throws the tank away from himself with a speed of 2 meters per second. With what velocity does the astronaut start to move off into space? Okay, cool. So again, I like to identify the action here to make sure I know what the before and after state is. And he throws this thing here, so there's my action. And if I can spell action today, wow. So there's my action. So now let's go ahead and do before and after for each of these cases. Before and after. So this is a challenging problem only for drawing. So how do I draw an astronaut? Let's see if I can do it. Can you draw an astronaut? Maybe I can use colors and put like a helmet on them. Oh, okay. They don't really have antenna like this, but I'm going to put an antenna just because it looks nice and cartoony. We'll just leave it at that and give them a nice little smile here because they're in space and they have some hair underneath that helmet there. Okay. And they are currently holding on to a tank of oxygen here. Or is it? Yes, an empty tank of oxygen. Usually there's like some sort of valve on the top here, so I'll kind of put that valve there. Maybe I'll label it O2 for tank of oxygen. It's a diatomic molecule. You remember that from chemistry? Okay, so then he throws it, and I'm going to copy this thing because I'm not going to get that anywhere close to being able to replicate exactly what I look like. And paste that there. Okay, cool. And so now I'm going to take this thing, almost, and now he threw it over there. So now if he threw it, it goes at a speed of 2 meters per second here. So this guy has a speed of 2 meters per second. Notice we know the speed of the astronaut itself. He said that he was at rest at the beginning, so this velocity here is 0. He's currently holding onto that thing, so I know that that velocity is 0 there as well. So then the question is, with what velocity does the astronaut start to move off into space? So question is, does he start moving because he threw this thing? Well, let's go and see what momentum has to say about that. Let's make our system here. And again, you can make your system anything you want. I'm going to make it both things, all the things that are interacting and transferring motion or momenta between one another. And so that's the both person, or I could say astronaut, and the O2 tank. Now, if that's true, I know that the change of momentum of everything there must be 0. We can't create or destroy momentum. So therefore, the momentum at the beginning must be equal to the momentum at the end there. And the momentum at the beginning, well, that's the momentum of the person and the O2, maybe I'll write it like that, together. I could think about that as two separate things, or I could think about it as one thing. It doesn't really matter. But I know that they're connected there, so they have to be moving together, so they have to have the same velocity, and that's how I know that I can combine them. Afterwards, they're two separate things here, since they're maybe moving at different speeds there, and we'll find out. And so I'll label it like that. Oh, and this is like the not, so it's at the beginning there. So let's go, let's see if we can expand this out. That's the mass of the person O2 tank at the beginning. Well, that's going to be the mass the whole time. We're assuming the mass isn't changing. And the velocity of the person O2 tank, and then at the beginning. And similarly over here, that's the mass of the person times the velocity of that person plus the mass of the O2 tank times the velocity of that O2 tank. So if we reread the problem here, do we know any of these values here? We know that the mass of this person here is 80 kilograms. We know the mass of the O2 tank there is 10 kilograms, and we know the speed of that O2 tank, so I'll go ahead and label that. That's the speed of the O2 tank there afterwards. We also know the beginning velocity of those things. Now, I could simplify this right here and go, hey, the beginning velocity of both of these things is just 0. 0 times anything is just a big fat 0 on that side. So that means, wait, hold on, before I even put in the numbers, that means that everything on the right side's got to add up to be 0. Well, let's do the O2 tank since we know something about that already. We know the O2 tank is the 10 kilograms, and again, I'll drop out the units if they're already all in standard units anyways. The velocity there, we said, what gave it to us, it was 2 meters per second. And it's going to the right there in our picture anyways, so that specifically is a positive 2 meters per second. So now, wait, hold on. This whole quantity right here is going to give me a positive value, and the only way I can add it to anything else and get 0 is that this thing's got to have a negative quantity. Well, mass can't be negative for the person, and I know it's not. It's 80. But the velocity of that person has to be negative, and mathematically it has to be negative. Let's see if that makes sense in our problem. If they throw the O2 tank to the right, that means that they're going to be moving to the left. Oh, yeah, that should make some sense, right? You could imagine that if you were on like slick ice or roller skates, and if you push something away from you, you'd start rolling or sliding the other direction there. Yeah, and that really happens. This really happens in space. There's some good examples in the movie Gravity. If you see the movie Gravity, or if you want to look up some YouTube clips of that, Wall-E has a good example of that. He's not throwing the O2 tank. He actually has a fire extinguisher, and he's firing the fire extinguisher. And so all of this like gas is coming out of the fire extinguisher. And that gas that comes out of the fire extinguisher, does that have mass? Sure does. So, and it's moving? Yes, it is. And so does it have velocity and mass? Yes. And that means that it's got some momentum. And so if I'm like holding onto this O2 tank and just merely letting all of the O2 out, or the fire extinguisher in Wall-E's case, and letting all that stuff out, I'd have a lot of momentum moving, let's say, to the right, and then he must be then shooting to the left. And that'd be really true. There's another really good example in the movie Passengers. It's a little bit newer. It's towards the end there, and he has to go outside the ship and do some things, and I don't want to give anything away there, but it's got some really good examples there if you want to watch that movie. It's actually a pretty interesting movie, and I enjoyed it. And or you could YouTube some of those ending clips there. Okay, so anyways, back to this. The astronaut's got some mass of 80 kilograms, and we don't know the velocity of that person there. And so now we can grab our calculators and just go do that. Subtract that negative 20 there over to the other side, divide by 80, and I get a velocity for that person of negative 0.25 or 1/4 meters per second. And so then I think about that in this context. Does that make sense? Well, one, we already said it made sense that it's negative. Does it make sense that he's going slower than the O2 tank? Well, he is way heavier, 80 kilograms versus 10 kilograms than the O2 tank, so that should make sense. I throw a really light thing away, and I'm not going to be moving as fast as that light thing. I was able to throw that. Well, you could even see that on Earth here. If you take a light thing like a baseball, even if you pitch that really fast, it doesn't throw that person to the other side of the field. He does get pushed backwards. That pitcher does get pushed backwards, but he's also pushing against the ground, and it's a relatively small amount that he can push against the ground and stay firmly planted on the ground. Similar to that fireman in the fire extinguisher, or fireman in the fire hose, but a little bit less extreme of an example. It'd be a lot easier to stay firmly planted on that, being that pitcher. Okay, cool. Well, that's it for this problem. Have a beautiful day.